So when we're looking for the area of a region that's enclosed between two graphs and we're not given any sort of interval, what do we need to find? What's the first thing we need to find?
Like where they intersect.
Exactly, and we can do that by just setting the two functions equal to each other. So we'll say 2 cosine x is equal to x squared minus 1. And we're going to have an issue with that because I'm pretty sure that none of you are going to be able to really easily solve that equation, since it's not just a nice quadratic, or doesn't have any clearly evident solutions to it. We could, if we wanted to, subtract the 2 cosine x over and use Newton's method to approximate it. But they're not going to ask you to do that on the AP test. They'll let you use a calculator for it to find where these would intersect. And so you'll have a graphing calculator, not Desmos. And during the sort of intermediary period between the quarters, I'm going to post some videos about exactly how to do that on your graphing calculator once I get my graphing calculator to load back on my laptop, since it's currently not working properly. So for today, we're just going to use Desmos to find where those intersect. So you guys can see Desmos now, yeah? I hope.
Yeah, we can see.
Perfect. So there are the two graphs. There's x squared minus 1 in blue, and then in red it's y equals 2 cosine x. And Desmos is nice that it just gives us those points, right? 1.265 and negative 1.265 approximately. Obviously, those are, those expand out forever, decimal expansions, but we're going to round to the 3 decimals that it gives us on Desmos today. So if this was the AP test, you'd just write 2 cosine x equals x squared minus 1, and then you'd say that that happens at x equals plus or minus 1.265. And in order to find the area of that region, then all we have to do is integrate from negative 1.265 to positive 1.265 of the upper function minus the lower function. And so if we look at the graph again, the upper function is clearly the cosine function, right? Everywhere from negative 1.265 to positive 1.265. That'll be 2 cosine x minus x squared minus 1. Everybody good with that setup there? Okay, cool. I'll pretend that's a yes, since nobody said anything. And distribute your negative sign through. And obviously this integral is pretty easy to take, right? 2 cosine x minus x squared plus 1 is a pretty easy integral to find. But evaluating it positive and negative 1.265, you're going to have to use a calculator for. So no reason to even bother to take the integral by hand. You might as well just let your calculator evaluate the whole thing for you. And so hopefully you guys remember how I told you to do that. You go into the math window of your graphing calculator, and it should be option number 9. And then just plug that integral in and give me a decimal approximation to at least 3 decimals, because you'll always round to at least 3 decimals on the AP test for any of the calculator questions. So what do you get there?
$4.995.
Great. Easy enough? 4.995 units squared. Pretty straightforward?
Yeah.
All right. Now, I want to real quickly mention one other thing about this one, just one little trick we might use. What's something we notice about both of these functions? Anybody notice anything about these two functions or no?
It's symmetrical.
Yeah, they're both symmetrical, right? They're both symmetric across the y-axis. Functions that are symmetric across the y-axis we call even functions, right? So both of these are even functions. And since we're integrating from the same value on the left to the same value on the right, just the positive and the negative versions of it, if we wanted to, we could have only done half of that interval. So we could have gone from 0 to 1.265 and then doubled the integral. And that would give us the exact same value. So another option would have been, since they're both even, to do this. And we'd have gotten the exact same value that we did the other way. You don't need to plug that into your calculator if you don't want to, because it's definitely the same. And oftentimes this little trick is convenient because evaluating at 0 is often a lot easier. If this was a function that was like, we were doing -8 to 8, the arithmetic for -8 and 8 might be a pain once we evaluated our integral. But if we did 0 to 8, at least we'd only have to do the annoying arithmetic once, and we'd have to subtract some easier stuff the second time. Good or no?
Good.
All right. Any questions on that? Everyone's good? All right, next one. We've got the area in the first quadrant bounded above by y equals root x. That's pretty good. And on the bottom by the x-axis and the line y equals x minus 2. And so if we're talking about this region in the first quadrant, we are only talking about this little piece of it. Everybody agree with that graph I've drawn and recognize that that's the region? Are any questions on that being the region? Okay, so this region is a little different than all the other ones that we've dealt with in the past. And how is this region different?
Is it because it's not continuous?
Well, what do you mean by not continuous?
Or I guess maybe it's just because you drew it starting from 0, but I thought you'd like if it went to negatives.
Right, well, I mean, square root of x doesn't have any values to the left of x equals 0, right? So this is where that function starts. But now that's not what I was looking for here. What I was looking for is that it's bounded below by two different things. It's bounded below by the x-axis and by the line y equals x minus 2. So from 0 to this value, the lower function is the x-axis. But from this value to where they intersect, which we'll have to figure out in a second, the lower function is the line y equals x minus 2. So we have two different functions that bound the bottom of this region for different portions of it. Whereas everything we've dealt with before, yesterday, and the one we've done so far today, the same function bounded the bottom of that region, right? Bottom was always this x squared minus 1. The top was always 2 cosine x. But now, for part of this, the bottom is y equals 0 for part of it, and for part of it, the bottom is y equals x minus 2. See the difference there?
Yeah.
So what do you think we need to do then, since we have two different functions that represent the bottom of this region for different parts of it? Can I just integrate from 0 to this value and call it good?
No, but could you do that and then like subtract the triangles?
Yes, so that's one thing that we could do. And in fact, we're going to do this same problem a couple of times. And that's one of the ways that we're going to do it. So we can do that way first. Talking about if we just did square root of x from here to here and then subtracted that triangle, right?
Yeah.
Okay. So if we were to just integrate the square root of x from 0 to, well, we got to figure out where those intersect. So where does root x equal x minus 2? That should be a pretty easy x value to find.
4.
Yeah, just at x equals 4, right? So if we just integrate root x from 0 to 4, we should be able to then subtract off that triangle. I'll sketch that triangle in blue. We should be able to find the area of that triangle. Right, so where does y equals x minus 2 cross through the x-axis?
X equals 2.
X equals 2. So we know the base of that triangle is 2. So it's 1/2 of 2 times the height. And what's the height of that triangle here? If I'm going from 4 up to the value at y equals x minus 2, that's 4 comma 2, right? That's a height of 2 also. So this integral with this area expression subtracted from it should give us the area that we're looking for in green. Good or no? Yes. All right. So root x, that's x to the 1/2. So when we integrate that, that's 2/3 x to the 3/2 from 0 to 4. And then we'll subtract 2. And if we're going to do 4 to the 3/2, that's the square root of 4, which is 2, cubed is 8, times the 2/3, which is 16/3, minus, when we plug in 0, minus 0, and then minus that 2. And 16/3 minus 2 ought to be 10/3. Good or no? Any questions on that? Okay. In fact, that way is probably the easiest way to do that problem, but we're going to look at some other ways that we could do it as well. So here's root x again. Here's x minus 2. Same deal. There's 2. They intersect at 4. What if I found this entire region first and then cut off this piece? Would that work too?
Yeah.
Yeah, that should also work, which is telling me that I need to integrate from 0 to 4. Root x is always the upper function, right? And what's the lower function? It's always this linear piece, right? If I'm including this little triangle down here to begin with. So minus x minus 2 from 0 to 4. And then we'll still have to subtract out this triangle, which is 1/2 of the base, which is 2, and the height, which is also 2. Good or no? And with any luck, this integral should come out when we subtract this 1/2 of 2 times 2 to it again. It should come out to be 10/3 again. So the integral of root x, like we said before, is 2/3 x to the 3/2. And then this is a minus x, which will become a minus x squared over 2, and then a plus 2, which will become a plus 2x. And we'll go from 0 to 4, and then we'll subtract 2. And if we plug in 4, what's 2/3 x to the 3/2? We did that a minute ago, right? That's 16/3. Minus 4 squared is 16 over 2, which is 8. Plus 2 times 4, which is plus 8. Minus 0 plus 0 for evaluating it at 0, minus 2. And now we've got 16/3 minus 8 plus 8. Those cancel, right? And then minus 2. 16/3 minus 2 is once again 10/3. Good or no?
Yeah, all good.
Yeah, a little bit more arithmetic to do, but it still comes out to be the same answer. Now, we're going to do the same problem, but a little bit different way. Sometimes we might not have these nice little geometric shapes to subtract. So we're going to pretend like we didn't see that, or like we didn't have nice little geometric shapes to subtract, and see if we can still find a way to do that. So there's root x, and there's x minus 2 again. There's 2 and 4, right? still -2 there. And this time we're not going to add anything in. We're just going to do this whole thing, but it's going to require two different integrals. So what we need to do is we need to split it at the point where we switch from one function being the lower bound to the other function being the lower bound. So we're going to have one integral that's just the integral of root x from 0 to 2, right? Because that's just the area underneath this function root x from 0 to 2, right? Everybody good with that? That's the first half of it. And then the second half of it ought to be an integral from 2 to 4 of the upper function root x minus the lower function, which is now x minus 2. And this way, if we didn't have nice geometric shapes, if this was a curve underneath it here that was maybe two different curves that were bounding the bottom, this is how we would have to set it up. Everybody see that? You good with that or no?
Yeah.
Good.
Cool. This way is going to require a lot more arithmetic and be a little bit of a pain, but what should we still get?
10/3.
We sure better still get 10/3. So root x, like we said, is still 2/3 x to the 3/2 from 0 to 2. And then we'll add to that, root x is still 2/3 x to the 3/2 minus x will be minus x squared over 2. And minus -2 is a plus 2, right? So that'll be a plus 2x. And we'll do that from 2 to 4. So 2/3 x to the 3/2 is just 2/3 of 2 to the 3/2. We can evaluate that later if we need to. Minus 0. And then plus, when we plug in 4, we already knew that 4, when we plug that in there, is 16/3, right? Minus 8 plus 8. And then when we plug in 2, that's again 2/3 of 2 to the 3/2 minus 2 squared over 2 is 2, and then plus 2 times 2, which is 4. And we'll note that we've got a 2/3 of 2 to the 3/2 and a minus 2/3 of 2 to the 3/2, so those will cancel. Minus 0 we don't need to worry about. Minus 8 and plus 8 we don't need to worry about. And what do we have? We have 16/3 minus -2 plus 4, which is 16/3 minus 2, which is good or no? Great. All right. And just when it seemed like there wasn't any other way to do it, let's do this problem one more time. And this way is very important for us to understand how it works. Sometimes, if one function represents the top, but two different functions represent the bottom, or you might have two different functions representing the top and one on the bottom, it might be too complicated to do it in terms of x, and we might need to change the outlook that we're going to have on this and try to do it in terms of a different variable. We want to try to do it in terms of y. So we can integrate in terms of y if one function is always to the right of the other for all y values in the region. So if we look at the region that we're interested in here, pick any y value between 0 and, what do we say, this goes up to 2, right? Pick any y value between 0 and 2. Which function is always to the right of the other one?
X minus 2.
Right, x minus 2 is the linear one, is always to the right of the root function. And so we will always do the right minus the left. Okay? But we have to do it all in terms of y, which means that we need to figure out if y equals x minus 2, what does x equal?
Y plus 2.
Y plus 2. And if y equals root x, what does x equal?
Y squared.
Y squared. So our rightmost function is y plus 2. And our leftmost function is y squared. So we do right minus left dy. And we integrate from the lowest y value of our region, which is
0.
0, to the highest y value of our region, which is
2.
2. And this hopefully will still give us 10/3. Y squared over 2 plus 2y minus y cubed over 3 from 0 to 2. 2 squared over 2 is 2 plus 2 times 2 is 4 minus 8/3. And then all of these are 0 when you plug in 0. So 0 plus 0 minus 0. And that gives us 6 minus 8/3. 6 is 18/3. 18/3 minus 8/3 is still 10/3. So it's really important that you understand how to integrate in terms of y, because not every year, but some years on the AP test, you have to be able to integrate in terms of y to solve a problem or two. And we'll do another one here in just a second. There's a few like this on your homework too. So very important that you understand how to integrate in terms of y to find area. Any questions on that? All right. I think that's enough for this problem. We could do it some other ways if we wanted to, but I think we've probably done enough. So let's take a look at the area of the region enclosed by y equals x cubed and x equals y squared minus 2. So let's graph these. We got y equals x cubed and x equals y squared minus 2. And just zoom in on this a little bit. And in fact, what I'm going to do real quick is just so I can annotate on it, I'm going to put it over here into our document that we're working with. All right, so there's our graph. And we'll go back to Desmos in a minute to take a look at what the intersection points are when we need them. But if we look at this region that we're looking at here between the two, right, all of this, for some of the x values, for example, at x equals negative 1.5 right here, the x equals y squared minus 2 is the upper bound. It's also the lower bound. That's a little bit of an issue. That complicates things and makes it more difficult. And for some points, like x equals 0, the upper bound and the lower bound are different functions. That's fine. But because some of them are the same function, it's probably going to be easier to do this problem in terms of y. So then we want to look for every y value between -1 and whatever this y value is up here where they intersect the second time. For every y value between there, is one of the functions always to the right of the other?
Yes.
And the answer should be yes. The cubic one is always to the right. Yeah, the cubic is always to the right of the parabolic function. And so we can do the cubic function in terms of y. So what does y equal if, sorry, what does x equal if y is x cubed?
cube root of y.
Cube root of y. We can do that cube root of y minus y squared minus 2 dy integrated from the lowest value, which is what?
-1.
-1 to the highest value, which we'll have to go back real quick and look at Desmos at what that was. The highest value was 1.793. And integrating this function is pretty straightforward, but evaluating at 1.793 is going to require a calculator, so we might as well just let the calculator do all of the heavy lifting there and figure out the integral and evaluate. So I'll let you guys plug that into your graphing calculator and tell me what you get.
Four 4.215.
4.215?
Yeah.
Great. Anybody have any questions or issues with that?
Looks good.
All right. We're going to do a couple more problems. We're going to do these ones back in terms of x now, but they might get a little bit more complicated here. So we want to find the area of the region or regions bounded between this parabola, 2x squared plus 10, the linear function 4x plus 16, and the vertical lines x equals -2 and x equals 5. So I think first off, our best bet is to graph each of those. So we got 2x squared plus 10. We got, what was it, 4x plus 16. And x equals -2 and x equals 5. And I'm going to need to zoom out a bit here and come up here. But we'll note that, zoom that down even more, there are multiple different regions that we are looking at here, right? There is the region between, and I'll zoom in, I guess, to show each region. There's the region that is bounded with x equals -2 on the left. The top is the parabola and the bottom is the linear function. Then there's the region that just includes the parabola on the bottom and the linear piece on the top. And then there is this other piece up here that includes the parabola on the top, the linear on the bottom, and then to the right is the vertical line. Everybody see all that? Good with that? I know it's a little bit of a mess there with all those graphs on there, but does that make sense?
Yeah.
So how many different integrals are we going to have to use to find this, or the area of these regions?
Three.
Should need 3 different integrals. First one should be from -2 to the first intersection point that we had between the parabola and the linear piece. And so if we go back to this, where did the parabola and the linear piece first intersect? At x equals -1, right? So the first integral will be from -2 to -1 with the upper, the parabola, minus the lower, the linear. So -2 to -1 of the parabola minus the linear. Second integral will start right back up at -1, and we'll go to the next intersection point between the two of them, which is at x equals 3. So -1 to 3, and this time, which one is above the other one?
The linear one.
The linear. So we'll do 4x plus 16 minus 2x squared plus 10 dx. And then the last one here will be 3 to our furthest right limit, which is 5. And this time the parabola is back on top. And we have that integral. Good or no?
Wait, can I see the graph again, please?
Sure. If you need me to zoom in or out or scroll up or down, just let me know.
Okay, I'm good. Thank
You
you.
good? Okay, cool. And so obviously we could simplify each of these expressions down and integrate them and plug in all these numbers, but that's a lot of arithmetic. And for 3 basic integrals, I'm not gonna even bother. I mean, this was the test or the quiz, or if this was a homework assignment, yeah, evaluate it out. If this was the AP test, yeah, evaluate it out. But that's our setup. That's the important piece. I think you should all be able by this point to be able to integrate each of those and evaluate them. So everybody good? Any questions on that one? All right, last one, and then we're done for the day. So we want the area of the region or the regions enclosed by sine x and cosine x, as well as the vertical lines x equals 0 and x equals pi over 2. These ones are pretty easy to graph, so I think we can do this without Desmos. There's sine x. There's cosine x. There's x equals 0. And x equals pi over 2 should be, well, that was not very well drawn, at the max of cosine, sorry, the max of sine and at the x-intercept of cosine. And so we'll note that, I'll label these sine x and cosine x, that we have a place where those two functions intersect. And on one side of that intersection point, cosine is above sine, and the other side of the intersection point, the opposite is true. Sine is above cosine. So we're going to have to do 2 different integrals to get the area of both of those regions. So what should the first integral look like? It should be an integral of which one minus the other one?
Cosine minus sine.
Cosine x minus sine x dx. And we're going to start at x equals 0. And where do those intersect? When does sine x equal cosine x?
Pi over 4.
Yep. So we'll integrate from 0 to pi over 4. And then we will add to that an integral from pi over 4 to pi over 2. The opposite. Now we have sine x above cosine x. Good or no? Okay. So what's the integral of positive cosine? Positive sine. What's the integral of negative sine?
Cosine.
Positive cosine. Good. From 0 to pi over 4. And then we'll add, what's the integral of positive sine? That one should be negative cosine, right? And the integral of negative cosine should be
Negative sine.
negative sine. And we'll go pi over 4 to pi over 2. A little bit of evaluation of these trig functions, and we should be good. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is also root 2 over 2. Minus sine of 0 is 0, and cosine of 0 is 1. And over here, negative cosine pi over 2, well, cosine of pi over 2 is 0. So that's just 0. Minus the sine of pi over 2. Sine of pi over 2 is 1. And then subtract this. So negative cosine pi over 4 is negative root 2 over 2. And then minus another root 2 over 2 for the sine. What's root 2 over 2 plus root 2 over 2?
Root 2.
Right, it's 2 root 2 over 2, which is just root 2. Minus the 1. Minus another 1. And then minus to both of these, which makes both those positives. So that's plus another root 2. And we end up with 2 root 2 minus 2. Good or no?
Good.
All right, that is everything we are going to do with area. Area in the plane, area between curves, area of multiple regions with curves that intersect, all that stuff. Any questions on any of that?